Hello. So for today, I took a problem from Rudin's Principles of Mathematical Analysis, and I added a new condition that the elements of the tuple y or x are 0. That is, well, making the problem a little bit more difficult, so let's review it. Let's begin with the base case, only this part from the textbook. And this can be proven fairly easily, inductively. Let's first review the case k equals 1. So the vector product of x and y is going to be x1 times y1 equals 0. And now thing is, since y is not equal to 0, y1 is also not equal to 0, so this implies that x1 equals to 0. So it is only true for k1 if x equals to 0. We have reviewed that case. Now let's review the case with the k is greater than or equal to 2. So we have x1 y1 plus x2 y2 equal to 0. x1 equals x1 y1 equals negative x2 y2. Now if x1 is equal to 0, that implies that x2 y2 is also equal to 0, which in turn implies that well, for one, it can be satisfied to say that y2 equals to 0, y1 equals to some number c, so that's not a problem. For x2, it's analogous. If x2 is equal to 0, then, well, a solution of another form exists. Y is equal to c 0. And well, if x1, x2 equal to 0, then any y would suffice, so I'm not even gonna review it anyhow. So now that we have this sorted out, we can suggest that neither x1 nor x2 are equal to 0. So what we're gonna do is we're gonna divide both sides by negative x2. Well, we can divide it by just x2. x1 over x2 times y1 equals y2. And now what we can do is we can pick an arbitrary y1. y1 equals c, not equal to 0, and y2 is gonna be x1, x2, c, which is, well, also not equal to 0. So a solution exists. Now we just have to show through induction that that'll work for all vectors. So what we're gonna do, we're gonna write down the scalar product in this form: j1 to k xj yj. We say that it's equal to 0. Now what we're gonna do is we're gonna grab some nice notation for a second, and I'm gonna redefine the exponentiation and rotation notation for my usage. Let's say that y to the power of 1 is just okay, wait a second, y to the power of 1 and y to the power of 0. Y to the power of 0 is vector let's call it U, that belongs to vector space RK minus 1, and Y0 or Y1 is a vector, let's call it V, that belongs to RK, yeah? So I have redefined it for my notation's sake. Now what we're gonna do is we're gonna say, yeah? We're gonna say that this is something true. So here we will say Y0. So for induction, we're gonna say that this works. What we're gonna do is we're gonna prove that this works too if this works. So let's begin with that, and now let's deduce this. Now what we're gonna do, gonna say gonna separate it like that, say k minus 1, and add x k y k. Now thing is, we can simply go ahead and say that y1 is gonna be equal to y0 in some sections. So we have implied this already. What we're gonna do is we're gonna pull out this single element one more. We're gonna say that j is not equal to I, and add this element xi yi 1 plus xkyk equals 0, and we say that I lies here. Okay, now what we're gonna do is we're gonna say that for y1 j gonna be equal to y0 j for j less than k and j not equal to I. So what we have here is we can go back here, we can rewrite this plus x j, not j, I y I 0 equals 0 and j not equal to I. So we have done that, and now we can work with this again. We can simply say that this is gonna be minus this, and then we transfer it to this side. What we have here is xi y1i plus xk yk equals xi y0i. Okay, now what we're gonna do is we'll transport this to the right side. Xk yk equals xi times y0i minus y1 I. And next what we're gonna do is we will divide both sides by xk. Yk equals xi y0i minus 1 y1i over xk. Reason we can divide by xk is the fact that if it were 0, then this equality would match easily with no troubles. We could just go ahead and equate y1 I to y0i, and it will work. So don't really care about that situation. So you can see that we have this part over here. Now again, this is an important part. We could not this is an important part. We could just go ahead and take some y equals 0, 0, 0, the dots, 0, and then some element I and j, right? And then we could solve this easily, like in the first example. It'll be equivalent, but since I added this condition, it's fairly easy to get lost in this. But again, I can still inductively show that it's possible to work with. So, since we're working with induction, we're implying that we could choose the tuple for previous spaces, so y0 I is not equal to 0. We have said that no elements of x are equal to 0, so xi is not equal to 0, and even if there were, that the equation would match easily anyways. The reason I'm adding that restriction is because if all x's except for 1 are 0, then that will cause a problem. We'd have to imply that one of the y's is 0. So that's why I added in the original condition that x is also not gonna be 0 at any point of the tuple. I just thought it's an interesting problem. So what we're gonna do is we're gonna pick y1i equal to c not equal to y0i, which would imply that yk is not equal to 0. So we have shown that if space rk minus 1 has vector y as color product with which should be 0, then there exists vector y for k. So that's good to know. Now we need the base case, and we have already shown it here, except we have already reviewed the original problem. So we include the cases where parts of the x's are going to be 0. But again, when that's not the case, then this comes to term. So you can see both of them are, well, not equal to 0, so the base case is covered, and by induction, this condition is entirely matched. So that's it for today, yeah? Bye, yeah?